In our next presentation, we will discuss how to create a mathematical model to analyze load combinations for an elevated structure. Our structure model will be an elevated tank. Our horizontal vessel will be roughly the same shape and size of a shipping container. As such, the design analysis is only somewhat different than analysis performed for other uses such as storage container, field office, or residential use. The main difference between this horizontal vessel and another use such as storage, office, residence, is the fact that the live floor loads for other usage would produce a lesser vertical force compared to a full tank, with a liquid that approximates, or exactly equal, to the density of water. Using the hybrid English standard unit of the kilopound for weight, equals 1,000 pounds, abbreviated as kip, and standard length unit of the foot for length, kip per foot squared, for pressure. We are given the values of operating tank weight, 40 kips, and empty tank weight, 9.6 kips. From the given weights we may calculate the seismic force produced by the tank for both operating and empty condition. Similarly, we can calculate the wind-induced forces on the tank based on its projected area. We are given a seismic factor of 0.087, roughly 9% of structure weight for seismically induced horizontal force. This is at the lower range of seismic force based on geographic location and soil characteristics. We are given a wind load factor of 41.86 pounds per foot squared. This is at the higher end of wind-induced horizontal force based on geographic location. A tank model considers two main variables as far as vertical loading: the operating condition, tank is full of water or another fluid of similar density, and empty condition, tank is empty. The two main creators of horizontal forces we consider will be that of wind and seismic loads. The word earthquake and the word seismic will be used interchangeably, having the same meaning. We consider both wind and seismic loads regardless of whether or not the building is geographically located in an area likely to experience seismic forces. It would be safe to say that any structure will experience wind force, but seismic force probability would be based on physical location. However, all structures are designed to anticipate seismic forces regardless of location. It is only the coefficient of intensity for either wind or seismic that will vary from one location to the next. For wind force, the geometric shape and size of the vessel, and the height above ground, will be the variables that control the ultimate wind force. We define our x, y and z directions as follows. We see that since the profile area is greater in the z direction, we get a larger wind force of 5.90 kips. We get a lesser wind force of 1.63 kips in the x direction. For seismic, it is the weight of vessel plus the contents that will govern the ultimate reaction force. In other words, wind reaction is a function of structure profile, and earthquake reaction is a function of structure weight. It is also worth noticing that the seismic induced force is the same in the x and z direction, since seismic is a function of weight and not profile. We shall utilize standard sets of load combinations which attempt to identify the most vulnerable condition likely to occur, then modify our structure accordingly, to reach a stable design plus safety factor. As an example, for wind, it is the empty structure, tank is empty, which would produce a more vulnerable condition during high wind, since there would be less weight to hold the structure down. For earthquake, is the fully loaded condition, tank is full, which would produce a more vulnerable condition, since earthquake force is directly proportional to weight. We intuitively grasp that vertical forces will always be present to a greater or lesser degree. We also understand that horizontal forces on a structure will occur at some point during the structure's use, either by wind or earthquake. Our main focus of concern then becomes how much do these forces create a tendency to rotate on our structure. It is the tendency to rotate which we will give a name, a moment. Vertical forces may also create a tendency to rotate, but if we model our structure as if the center of gravity occurs at the geometric center of structure, we largely ignore the vertically induced moment. A vertical load, not at the geometric center, produces eccentric loading which we will not consider in this first example. Having introduced the concept of a moment as a form of rotational tendency, we may also consider that we will want to analyze a moment, rotational tendency, around various axes of rotation, depending on which influence on the structure we intend to study. The unfactored wind and earthquake loads are listed. Horizontal loads may act in either plus or minus direction. Force times moment arm gives corresponding moments. We will now introduce the load combination standards. There are two sets of standards, ASD and LRFD. We will use both ASD and LRFD to illustrate the procedure. The short explanation for the ASD versus LRFD model for load combinations is this. These are two similar mathematical models. There are different load factors applied to the estimated horizontal and vertical forces in ASD versus LRFD. The two mathematical models use the same variables. The variables are the horizontal and vertical forces, estimated to occur based on the weight and profile of the structure. In this particular case, the structure is a horizontal vessel. We start with ASD standard. In our example, we have a horizontal vessel. There are no floor live loads nor roof loads. We also will not consider rain or snow loads. In fact, several of the listed loads from ASD are not applicable to our structure. We show underlined the applicable loads and combinations. We further refine the load case list by omitting the non-applicable loads. For our case, the D plus F loads, dead plus fluid, may be replaced by WEO, weight of equipment, operating. As further explanation of ASD and LRFD load cases, we look at these as two mathematical models. As engineers, we understand the load case list attempts to model a physical condition, or several physical conditions, as we change forces in one of four directions horizontally and in one direction vertically, creating snapshots of several cases. There is a standard International Building Code, IBC, which interprets and presents a common version of ASD and LRFD load case list. The United States ASCE, American Society of Civil Engineers, has suggested some additional modification of ASD and LRFD load cases for the seismic loads. The ASCE modification increases or decreases the vertical component of weight as effort to create a more conservative code. We label horizontal forces coming from four directions and one vertical load. We also note the group of load cases specific to our tank model for ASD case list. At first glance it appears we have created 29 load cases, first case with only vertical loads, plus 4 horizontal directions for each of 7 cases. We added additional load cases, for what appears to be redundant, X and Z horizontal forces, in the plus and minus directions, for each of 7 categories of load cases, plus 2 additional load cases for vertical load, resulting in 51 load cases for this ASD tank model. We will start with load case 201 as first load case and up to load case 252 for this ASD model. Additionally, we attempt to differentiate between wind and seismic load cases using green for wind and purple for seismic load cases. The first group of ASD load cases involves the operational tank weight plus 60% of wind. Greater force in the Z direction means greater moment about the X-axis. We summarize our result for full tank weight, WEO, plus 60% wind. The maximum rotational tendency occurs around the X-axis, with a result of 23.37 foot kips. The next ASD load combination to consider is operating weight plus 70% seismic. Tank operating weight is factored up by 3%. The expression is 1.029 WEO plus 0.70 EO. For seismic force, we get the same value in X and Z direction. Seismic force is a function of the vessel weight plus the weight of its contents, WEO. The seismic force is assumed to act at the center of gravity. Given WEO, weight of equipment, operating, equals 40.00 kips. And WEE, weight of equipment, empty, equals 9.60 kips. From which we calculate the force for both the empty and operating conditions. In this case, we use the force from the operating condition. We multiply by the 0.70 horizontal ASD factor, and also multiply by the earthquake moment arm, to get the moments around the X and Z axis. X and Z forces are equal to one another. The rotational tendency is also the same around the axis. We summarize our result for full tank weight, WEO, plus 70% seismic. The maximum rotational tendency occurs around either X or Z axis with a result of 21.32 foot kips. Our next ASD load case will be to consider 0.571 WEO plus or minus 0.70 EO. Or to say in words, let's apply a factor of slightly less than 0.60 to the vertical component of force, while at the same time, let's apply a horizontal factor of 0.70 to the horizontal component of force. In this series, we are once again considering seismic action as the creator of horizontal force. It should be no surprise that the X and Z forces are the same for this numerical series, as the last series, since we are considering the same 0.70 factored seismic force, which in turn also created the same sets of rotational tendencies. It is the vertical force which changed for this series of load combinations. In this case we considered load cases 220 to 227. Our next ASD load case will be to consider 0.60 WEE plus or minus 0.60 FW. In words, let's apply a factor of 0.60 to the vertical component of force, using the empty tank condition. While at the same time, let's apply a horizontal factor of 0.60 to the horizontal component of force. In this series, load cases 228 to 231, we are considering wind action as the creator of horizontal force. Additionally, 0.571 WEE plus or minus 0.70 EE. Let's apply a factor of 0.571 to the vertical component of force, using the empty tank condition. While at the same time, let's apply a horizontal factor of 0.70 to the horizontal component of force. In this series, load cases 232 to 235, we are considering seismic action as the creator of horizontal force. When reviewing the result for last 8 load cases, as we would have expected, seismic forces were reduced since seismic force is directly proportional to weight, and it was the empty tank load case factored at 0.60. Seismic load cases produced lower forces and moments than what was the case for the full tank. For wind, the same tank profile exists regardless of empty or full tank, therefore we get a larger wind-induced rotational tendency for 2 of 8 load cases. The next ASD load combinations are 1.00 WEO plus or minus 0.45 FW. Apply a factor of 1.00 to the vertical component of force, using the full tank condition. While at the same time, let's apply a horizontal factor of 0.45 to the horizontal component of force. In this series, load cases 237 to 244, we are considering wind as the creator of horizontal force. The final ASD load combinations are 1.021 WEO plus or minus 0.525 FEO. Apply a factor of 1.021 to the vertical component of force, using the full tank condition. While at the same time, let's apply a horizontal factor of 0.525 to the horizontal component of force. In this series, load cases 245 to 252, we are considering seismic as the creator of horizontal force. Having assembled a table of ASD loading combinations, there are 2 variables from the results table which become main items for evaluating each loading case. The 2 main variables are the summation of vertical force, sigma Fy, and the summation of rotational moment, sigma m. The summation of vertical force sigma Fy is equal to the weight of equipment plus weight of foundation. The summation of rotational moment, sigma m, may be considered as the maximum encountered rotational moment based on the particulars of the load case. The tank model is presented here as a free body diagram. The moment force may be replaced by an equivalent reaction force, Re, acting at a distance, E, from the axis of rotation. We get a different value of E in the X and Z direction, Ex, or Ez, and the resultant base pressure is maximum either along the LFX or LFC direction, either along the longer or shorter length of foundation, but since it is the half width of foundation that must resist the overturning moment, we expect the higher base pressure to occur along the shorter edge of foundation. It is worth to scroll down to view the ASD load cases and subcategories for groups of load cases. There were several variables which were used. In this type of analysis, the maximum base pressure may occur at a load case which was not intuitively obvious. Keeping in mind that various vertical and horizontal load combinations, moment arms which create rotational tendency, lengths of foundation in X or Z direction, all come into play when determining the critical load combination. In our case, it was load case 216 which produced the maximum base pressure of 895.41 pounds per square foot of base pressure. Another load case of interest shall be that which provides the least factor of safety for overturning moment. The restoring, referred to here as righting moment, Rm, is equal to the summation of factored vertical force multiplied by the half width of foundation in the LFX or LFZ direction, depending on which axis we are calculating the righting moment, Rm. For our ASD load cases, the least factor of safety occurred at load case 230. It is worth to notice which load case produced the most unstable result. It is the case 0.60 WEE plus or minus 0.60 FW, where the empty tank was modeled, plus an additional 0.60 ASD vertical load factor, to further reduce the modeled weight of empty tank and foundation. The ASD model says, let's apply a 60% wind force to the lightest factored weight structure. So the factor is 0.60 in both horizontal and vertical direction for this ASD case. Since wind force is not a function of weight, the wind-induced moment is significant in this case. We will now introduce the LRFD group of load combinations, and compare to the ASD group of load combinations. The basic difference is the fact that LRFD tends to omit the horizontal load factors. For wind or seismically induced moments, the factor is assumed to be 1.00. LRFD load cases feature a slightly increased set of factors for vertical forces compared to ASD. Otherwise, the basic variables remain unchanged from ASD to LRFD. The general result is, the LRFD model predicts higher pressures and reaction forces, therefore is considered to be a more conservative model. As engineers, we want to have a working knowledge of both ASD and LRFD load combinations. We consider the physical model and make an engineering judgment about which LRFD load case produces the critical result. In this case, it was load case 115 which became the load case of interest. Our main reason for analyzing load case 115 was the higher max base pressure, maximum at end of foundation along X direction, due to full tank weight and seismically induced force and moment about the Z-axis, induced by seismic force along the X direction. The horizontal force creates a moment at bottom of vertical pedestals and a variable moment, maximum at the center of an idealized beam, subject to W-net loading, and modeled as a double cantilever beam. The table above shows wind and seismically induced force and moment values and maximum base pressures. We previously made the judgment that force along the X direction, moment about Z-axis, will produce the load case of interest based on the geometry of the mat foundation and vertical pedestals which span the width of the foundation. Seismically induced max base pressure along the X direction is greater than wind-induced, therefore becomes the case of interest, any among load case 112 to 115. In order to model our foundation as a double cantilever beam, subject to W-net loading, a conservative assumption is made that W-net will be the higher among the linearly variable pressure, using higher coefficient of pressure increase, W-max, and subtract overburden, weight of soil plus weight of slab, we arrived at W-net. Moment and shear equations may be obtained from beam tables, modeled for our specific loading. Shear and moment are variable according to X range, 3 ranges of variable X values. An alternate W-net2 is shown with still more conservative assumption. Use max base pressure in any direction or by any load case, load case 108, wind-induced moment along Z-axis, and a slightly different interpretation of overburden, produce the load case of interest. Moment and shear are shown graphically as function of X. The W-net is main input item, subject to several engineering judgments. Reaction R1 is a function of W-net. A slightly different set of engineering judgments produced a different, increased, W-net, and is considered to be an alternate, more conservative load case. It is worth comparing the two load cases, LRFD 108 and LRFD 115, to note the change in shear and moment based on a slightly different set of loading assumptions. Higher base pressure induced by wind load case 108 in Z direction, modeled as max base pressure in the X direction. Area of steel provided per foot is a function of bar diameter and spacing. A unitless rho value, defined as rho, can be derived from area of steel provided divided by area of force rectangle, BD, from which we may derive the unitless omega value, defined as omega. Moment capacity as shown is assumed to be in units of foot kips per foot. We compare moment capacity to maximum induced moment, referred to as max moment, and find that moment capacity is roughly 3 times that of max moment. Shear and moment curves are shown graphically. Our final observation for this LRFD analysis is that LRFD is the more commonly used when calculating internal moment and shear forces, either wind or seismically induced. Additionally, ASD analysis is commonly utilized for overall structural stability in its natural environment. In either case, an attempt is made to discover the load case which makes the structure more unstable or to approach its internal stress limits. This concludes our presentation for ASD and LRFD load case analysis.